And yeah, so welcome everybody. Now that I'm starting the workshop right now, this is the workshop for 232. Um, I'll be going over mainly the simulation assignment 2 that you guys have to do sometime these coming days. I'll try to keep it as brief as possible for anybody that is watching this as a recording, or for you that are here right now paying attention to me presenting it. Um, Main purpose I'm trying to get you guys is, again, to assist you in completing the assignment, but not to do it for you. It's mainly to just really walk, like, how to set up the entire circuit for you guys to then just solve it yourself. So, and to start off with that, we'll then also say that we will plan to do more for future simulation assignments, but we'll have to really see through attendance and who will be needing these workshops. So if you know anybody else in other classes that will are in need of help using these multi-sim workshops, or at least in some way or another, please let them know, because again, this is everything is for the students, for you guys to really benefit completely. So and again, it doesn't really necessarily have to be 232 students. If you are like some of you in the audience who just came to just learn Multisim, this is a good place to start. Um, so first off, the simulation assignment 2 is going to be based off pulse responses. So I don't know if you guys have gone over this in your classes recently for 232, uh, but it will mainly focus on the different signals that will go into first order and second order circuits. Uh, for today's workshop, this is going to be first order RL circuit. Um, and an assignment set up by laptop usually goes about considering a circuit, such as the one below, where we would choose our own values of inductor and resistor, and then we would be figuring out the transient responses throughout the RL system when the current source signal is in this form of the graph below. And you guys can see this, right? This is feedback that everything's going smoothly. You guys can see? Really? What the hell? Oh my god. That is embarrassing. What is happening? Oh, okay, whatever. Um, yeah, that was bad. It was on the wrong one.
Now we can see. Yep.
What happened?
Now we can see.
Yeah, so now you can see it. This was the introduction to the PowerPoint, but it's not much anything needed. This is the main one that you guys need to know to like just kind of start with. So again, start off again. Considering the circuit below, where we choose our own values of the inductor and the resistor, um, we're looking for the transient responses throughout this RL system when the current source signal is in this form of this graph right here. Um, it's more of just the shape and how it is that we will take advantage to then put in the multi-sim simulation. Same goes for the circuit, but the values of the components we're going to change to benefit you guys in understanding what is happening. Since this goes into differential equations pretty fast. Um, Convenience, we choose our resistor to be 1 ohm, our inductor to be 1 Henry. The period of the signal, which would go from this point to this point, is going to be 5 seconds. So it's the same for this one here. And then at the same time, our initial point of the start of our signal will be at 1 second. So it will be shifted to the right at 1 second. Um, and then additionally, all our variables that are already labeled are going to stay the same as the representation shows. Um, and we can already start calculating our tau, or time constant, of L over R. It's going to be equal to 1 second, because 1 over 1 is equal to 1. So hopefully you guys have already know this knowledge, and I don't need to really go into further explanation of why. From this, we then can also then start already, we will already be able to solve this analytically. And if we do follow the correct steps to finding the differential equations and solving the entire system, you can find that the piecewise function can be of both the necessary parameters for IoT is going to be 0 amps at a certain time interval. This function right here, oh, that's bad. Ignore that IoT, but 10 minus 10 for exponential of negative 10 minus 10 amps in this time interval, and the following here also. So if you can imagine how differential equations look on a graph, it usually is going to be like a piecewise function is going to be exponentially decreasing or increasing depending on what the actual factors are. And this also goes the same for the voltage across the resistor and then the inductor. So now that we know what are our main parameters that we were looking to find out look like analytically, we can then take the approach into Multisim. So I could escape. Okay. So I'm just gonna check like this. I go to the Multisim. So let's get this to work to my advantage. Okay. Setting up for this assignment will be requiring us to really be already in depth and or not in depth, having a background in Multisim before. In other words, you guys know where the components are and also what you guys can like fix, such as changing the variables. So just a quick thing, if you guys are not so sure, you would click and then you would go to the value and then you would input what your value for the component is. You guys can see this by the way too, right? Like this is clear and crisp. Okay, perfect. So following on with that, we are in need of actually representing our circuit through graphs. And usually Laptop prefers you having, in a sense, a really good and self-explanatory graph that doesn't require the reader who, we take an assumption, doesn't know what is happening, but will learn from the graphs and also your circuit below. Usually he also prefers you to have labels for everything. So he does take credit if you don't have that. So that's a warning if you guys have not learned or not learned, have not known about him. He's very strict with his KVLs and understanding his labeling because it's important for engineering overall. Moving on from that, start off, we are going to try to right now set up the graphing plots for IO. We also could do IR and IS. And we're also looking for the plot for V out or VO through time. To start up this, we need to find the actual pulse response component that could represent the signal that we already saw before in the presentation. Usually what you have to do is, these are kind of tricky to find if you've never used piecewise function sources. They're usually located in sources here. And then if you go to your signal current sources and not directly go that, it should usually be here, piecewise linear current or current. And it's the same for a piecewise linear voltage, where you could set up anything that is exponentially increased, not exponentially, linearly increasing, or constant increasing. So just like a stepwise like this. And you will have to use these for future simulations, specifically for if you do plan to do the extra credit project in the end, you will have a part where you use something similar. So when you then set up the actual piecewise current source, you have to make sure to input your values that kind of describe what the graph will show. So at time 0, current 0, and then at time 1 second, going to be still 0. But then at 1 second, it immediately shoots up to 10 amps. So if you could see from this, you can then take an assumption that you have to really know how to plot the points, so they're not too all over the place, because it does change a lot if you do have a misplacement in a point. So like, let's say I put this at 2. That's good, yeah. So if I keep it like that, and if you guys have not used to simulations yet, I go to transient, my output, I'll choose IS. So leave it like that. Just run. This isn't much of an actual like well put out type, or pulse response type function, because it's got a slope. This could represent other types of signals, but not the one that you would be looking for in the actual circuit. So it's something that you want to be sure to look out for. So moving on from that, additionally, if you do plan to do them, watch out for your maximum step, time step. Usually these are your deviations of how much calculation Multisim will do for each single point. Don't put too many, but don't put a lot, because sometimes it will load it really, really, really slow. Depending on what type of system you are simulating. If it's a simple system like this, it shouldn't take any longer than that. But it also depends on what your time interval is, or your time deviation is. But that's how you properly set up the actual piecewise function to your benefit of your assignment. Now, looking for that, we want to now actually start graphing our parameters that we're looking to really see how they behave in a transient response, especially with this signal. So, looking at the actual outputs again, we could then output our different signals that we want. So we want to see IS, which is our input signal, IO, which is the current that's going through the inductor, and then CO, which is the voltage across both the inductor and the resistor, and also the current source. Knowing that if you have practiced enough and seen the differential equations, you can already assume how this will behave, in the sense that after a long time, this inductor will become a short, and then it'll just kill off this resistor. So then this resistor won't even receive any current, and it'll just be an open circuit at the end. And all the current will just be going through the inductor after the inductor kind of accepts the current that's going through it. Depending on also how this pulse response behaves, because once the pulse response becomes negative, it changes everything. Once it becomes 0, it changes everything. So let's just see how the behavior turns out. So we can then already start looking at what our outputs or our graphs are and what they represent. So for the green, these represent the voltage. So you have to think about it in a circuit analysis way, that it's following rules and laws of physics and circuit laws. So knowing that an inductor becomes a short at the end, the voltage is going to start decreasing, because more current is going to go through this, but the resistor is not going to receive any current. So then no current is being dissipated, and then the voltage is going to decrease. At the same time, we know that inductor doesn't kind of have a set voltage drop, because of its what's the term? I don't know if I can on it. Well, it's transient response to it, because it becomes a differential equation, starts decreasing, and then it starts going to 0. But then once you switch it to an opposite current source, it's going to be going opposite to what the inductor wants, and then it flips it and then activates a voltage to be across the resistor and at the inductor. And then you just have to really see if it does follow it. And at the same time, after you do your analytical analysis, on by hand of the actual system. So if we compare it, it's going to help that we kind of see if it's making sense. So at zero time interval of t less than 1, which is around here, current 0. Same goes for the voltage. And then if you follow through, you can then see that if your interval is following the differential equation, and if not, you might have to either recalculate your expressions, or you have to kind of just see if your transient simulation is correct for the graph. Always be careful where you put your probes, because different positions of probes, especially at a common ground, changes what you're analyzing. So it's convenient that this circuit right here, all of the main nodes have a common ground. But if you take the one node and then you switch it to here, it's a whole different voltage. Actually, it's 0 because there's no voltage across it. So, for example, that's one kind of like big sample to really look at. Or if you for some reason move without noticing a current to be here and you're analyzing this current, it's going to be a whole different current going through this let's call it this ammeter. So also I can explain this is your ammeter probe or your current probe, and then this is your voltmeter. If you want to use an actual ammeter components, they have them here on the side if you see. But yeah, that's mainly how I like to really set up your circuit, or just the first part of what the simulation assignment will ask for. And then you kind of then also, he usually likes to ask you to graphically calculate or estimate the time constant. This is where it's important to also get used to using the graph viewer of Multisim, especially once you get later on into your other simulations. Um, you then start seeing that you could do this with cursor. So cursor allows you to see different points at the same specific points of time. So, and you could do comparison. You also have to make sure which of your functions is checked off. And then following with what I was saying, he usually likes you to graphically estimate the time constant. We already know what our time constant is on this circuit. So we usually want to find a common point where we can like see it, see where the time constant might be the same. And what you could do is you could set the x value of this to be, let's say, 0. No, not 0, 1. Set that to 1. And then, by the way, I'm right clicking on the cursors. There's two different cursors, so they'll be different. One's 2 and the other one's 1. Pretty distinguishable. No, 3. So if you keep, I'll keep it at 2. If you move the crosshairs to like the proper place, you then are able to at least see that there's also a differential part of the of the cursor. And one of the things that I don't know if he's mentioned in the class before for 232, before you started doing your first simulation, you could represent the, like in a graphical sense, what tau is, or the value of tau, as like a, looking for it, but as a ratio of two different points in the graph. So what he usually likes to say or represent is that the dy dx is also equal to, in the derivative sense, delta y over tau. And let's say that what you could do to find tau is that you can then do so and manipulate it and set up that tau is equal to delta y over dy dx. So delta y is usually the dy, but dy is kind of a limit of delta y approaching 0, I think, or no. In derivative sense, it's supposed to like reaching the smallest point of difference. What we know is that dy dx is 6.3212, and dy, which is in this case delta y, is 6.3212. So if you then do the math, you then figure out that dy, like this number over this number equal to 1. And that's the same thing that happens with dx, because you think of like fractions, dy or divided by dy over dx, it's going to still be equal to dx, and dx is set to be 1 here. And that's what our time constant is in the case of this assignment, 1 second. So usually you would have to label that by clicking it, not like that, but like just note it and then put that around this second, and this parameter here. Here, there's two different like cases. Well, this wouldn't be 0, but this would be like 10 technically. Then you would then explain it in your description of notes, your description of your circuit, that why this is the graphical representation of tau for the circuit. Yeah, and that's how you properly, or that's in a way, that's one way to actually represent the graphical tau, or the way I've done it before, and I've done good with using it. It's very useful also when you are just given a graph before seeing a circuit. Then there'll be one more thing I'll try to represent for you guys. Oh, so during these circuits, he might not give you the option to choose what your components' values are. So it's important to really know how the values of components affect your differential circuit, your differential equation. So especially with values like these, this simple, that are this simple. So values that are this simple here, like mine. So values like R1 and L1, these are very simple ones. It's pretty difficult to find a 1 Henry inductor in real life. But usually these type of expressions for the equations and the behaviors of the circuit won't be ideal. So if you do come across such as like this type of representation of a circuit with these actual values, you'll get a whole different actual like equation. So when comparing what your graph shows, you should see that it's actually following it. Sometimes you'll get a current relative to the voltage in milliamps, while the voltage is like hopefully not 100 volts. Your circuit will be a lot smaller. So like if I do this with this multisim, that I change this parameter to 3K, and then this one 75 millihenry. Yeah, my transient will look a whole lot different. But I'm not sure if it will for these specific ones, but just run it. It'll look completely different. But that's because of like relative comparison to one another. Especially since one and the other is not going to be the same. So I want to really see the actual circuit of the input of the piecewise current source, it'll look different relative to itself. But then if it's relative to V out, it's gonna be like so weird, right? But if I just focus on V out in this specific arrangement of for the circuit, it will actually still look weird because of the different time variable, the time constant. So the time constant is also a thing that affects this, especially with this input current, where this would be in 1 second intervals, while the time constant for the circuit will be about, I think, 25 micro. So it changes a lot. So that the time constant for this circuit would be a whole lot drastically different than other circuits. And that also kind of brings me into this, where like if you do label your time intervals in millis or micros, you got to make sure it's like applicable to your time constant. So I'll make this micros. So for convenience sake of the circuit. Yeah. 15U. Okay. So hopefully this is still pretty good. I have to see also my maximum time step because that changes a whole different aspect of it. Yeah. So it kind of changes a lot. I'm making these changes like on the spot, so it would if you do change your components without seeing the other parts of your simulation, it will result in stuff like this, where like it's a very indistinguishable graph and not even something that you can hand in. Um, so you have to really understand how your components affect your equations and like their intervals and their behaviors, especially in time. So if I go back to the original values, so if I go to the original values, well then keep it as 1. Yes, I'll go back to 1, 1, and 6. If I go back to the original values, it's just going to be the same. And hopefully the behavior didn't change drastically, but so yeah, it went back to being a normal representation of the circuit. Um, so your choice of components again affect how your graphs also look, and it's the same thing that goes with your graphs. It affects how your components appear to be. Another thing we can go about. Well, I think that's mainly what I could really show you guys for this simulation assignment. Since you guys are still learning of different um, RL and RC and different RLC circuits, so then see how the behaviors kind of change. Also, when you guys learn about control sources or dependent sources, you'll see there's also a difference in how your entire graphs change and also with the behavior of your arrangement of your circuit. Um, does anyone have any questions regarding this or anything they'd like to ask that I could not walk them through, but like kind of assist them for this upcoming assignment?
Hello.
Yes.
Just curious. So this piecewise current IS, that would be considered like a time varying current, right?
I'll repeat that again.
the IS, the independent current source, that's essentially a time varying current source. Yes?
Yes. So if you, as in that term, it's time varying because it's, if we just look at its behavior, it's
Yes, I imagine it would need to be time varying because if it's constant, then you wouldn't be able to graph it properly.
yeah, no, if it was constant, it wouldn't behave as well as you would like, especially for this assignment, since this assignment wants you to have a pulse response, and
Right.
this is what your pulse response of a circuit, um, with an
Hmm.
impulse response, with a pulse input would behave like.
Okay.
So, and this is a first order. This is a first order circuit. If it was second order, there's a whole different effect because that's where it gets to second order differential equations. Hopefully, most of y'all that are in this workshop have at least taken it or have at least some background into an introduction to differential equations. At least Calc 2. Calc 2 is the main thing that you would need. But I'd assume that everyone that's taking 232 has taken Calc 2. So yeah, like it's mainly the behavior that affects in like the circuit. So it is time varying because it's changing.
Right. Um, Two more questions.
Mhm.
Uh, One, so I know you're recording this. Do you
Yeah.
plan on putting this somewhere that we could view later at all, or?
Yes, we hope to make it a bit more organized. I will have to consult with people with other people in IEEE about how we're gonna make this available because we didn't want to. We're gonna make it public, so it's not something we're not gonna like allow you guys to look back when you guys need help. Because again, we're here to help EC students try their best and do their best in their classes. So
Thank you.
hopefully a link will be put out.
Okay, that makes sense. Thank you very much. And I guess
Mhm.
the last question is, this is a really simple one, but could you just show me the variables again in analysis in simulation? I just want to confirm something.
So what are you in particular looking for? Like my variables? So my
Yeah, I just wanted.
variables that, so
It,
yeah, you could go.
Sorry. So I'm assuming you just picked the variables. What was it? The V for what was it? Inductor and the current and the current source and I think there's a third one, but my vision's not that good. Uh, I can't really see the third one. I guess maybe
It's
that's just
IR.
IR. Oh, it's IR. Oh, my
So
bad.
this is the current going through the resisting. Usually how I denote or how I recommend other people when they're labeling their currents, especially time varying currents, um, I try to like make them respective to what their behaviors relate to. So this current goes through is time varying in relation to the resistor. This one goes to I. It's called I out mainly because in the assignment, this in this picture here, it's um, current's called I out. So you just keep it the same to what the assignment would describe it as. Same as the V out. V out is the voltage across the inductor, but actually the entire system since this is parallel.
Right.
So so what is specifically else do you have like a question towards the variable?
I don't think I have really anything else. I think I'm good.
Okay. So as long as this is like a clear thing, I'm still able to answer questions if anybody else in the workshop wants assistance in some way um towards understanding this.
Could you show me the graph one last time?
For which one specifically?
Oh no, just for yeah, that graph. What is
Yeah.
it? Thank you very much. Actually, could you show me the when they had the yeah, there you go. Perfect. Thank you very much.
Yeah.
Just
So
just to be sure because it has the okay. Thank you very much.
no problem.
And I guess ask one more thing. Like, do these correspond to the equations we saw inside the slides or no?
Yes. So if we
Good. Just
want
being sure.
to, yeah, if we want to make a relationship to it, these do represent each interval. So hopefully I can drag this and you guys can see it because these are small fonts and I am sorry for choosing small fonts. But for example, like how I said before, 0 amps represents in the interval less than 1 second 0 amps. So for I out, so I out is, wait, there's a difference. So I out is 0, but then once it reaches the interval of 1 second to 6 seconds, which is from here to here, it is exponentially increasing, but at a like negative value. So that's where like, so like let's see at, it's the exponential to the negative t minus 1 parentheses power. If you could see how I mean it, exponential is your e or your Euler's number, um, and then it's exponentially upside down or inversely decreasing, so it reaches 10. So once it reaches to 6, it should be 10. So when it's at 6, it should be at like about 0. Like, so exponential exponential to the negative uh, fifth power is about to like 0.0067 times whatever your factor is. So that'd be really small and negligible. Like if you zoom in, it's very small. So, and you kind of just assume already at that point it's about to be 10. And after a long time pass for that same equation, it will just reach 10. The number will be like decreasing ever so slowly, but you just assume it's 10. Same goes for then the next part, where after like the current or the current source becomes upside down, that's where it affects the entire like current across the inductor. It just goes the opposite way and then tries to go negative 10 in the interval of like 6 to 11. And yeah, it's represented to the different values. And then once it flips back to 0, then it just decreases because it gets dissipated by this resistor. Because now at that point of this interval from um, 10, no 11 to just infinity, it's just gonna be what you'll only be seeing is just the inductor and the resistor functioning. Well, just this would be already dead because it had no current to represent. Um, Same would go to the voltage, but the voltage, since this is an RL circuit, the current is not the current is the only thing that's continuous across the inductor, while voltage, it's non-continuous, so it could literally spike up like this every time. So does that answer your question for how they relate to one another?
Yeah, pretty much. Thank you very
Okay,
much.
no problem. Anybody have any other questions? Anything related? Well, I could then say that we've completed this workshop. Hopefully this has assisted you in some way for this assignment that's coming up for you guys. I know probably due Tuesday or something, I think. Or I don't know when you guys get your dates, because at the moment I know Levkov has like sometimes forget to post what the assignment asks for, but these first 2 to 3 assignments should not be too harsh on what you should be looking for in your graphs and what he's asking for. Just do make sure to like always hand it in on time so you get always the full credit. And you do understand what is happening for quizzes that he gives you, because sometimes he does make his quizzes based on simulation assignments. Sometimes, so I can't promise you that he will. So, yeah, so we could adjourn this workshop, and hopefully whoever's also watching the recording, they've also benefited. And I'll make sure to stop the recording. And yeah.